In this video, we will explore the topic of ultrasonic levitation, and specifically the properties of these high-amplitude sound waves that allow for this phenomenon to occur. To begin, we'll examine the setup of the system, which starts with 120 volts from a standard US outlet running into the transducer driver board. Before exiting the driver board and entering the transducer itself, the voltage passes through multiple transistors and transformers to amplify the voltage of the circuit to 550 volts AC and 36 kHz in the form of a sine wave. This voltage is then applied to an electrode within the transducer, which is surrounded on top and bottom by two piezoelectric discs, which will then fluctuate in size based on the voltage applied across their surface, which is oscillating from high to low at a frequency of 36 kHz. Sound waves are thus emitted by the transducer, and when reflected off an aluminum top plate, which is located at some increment of m lambda over 2, creates a standing wave, which has nodes of unchanging pressure and antinodes where the pressure will fluctuate from high to low. We notice that our levitated spheres in this visual are located just below our nodes of unchanging pressure, where we might presume they would rest. And so we must ask, what about these forces acting on the sphere is causing them to rest in this region? We know that each levitated sphere is experiencing a downward force due to gravity and a small upward buoyant force. Since the object is sitting within the antinode, at one instance in time, it will be in a high pressure zone, which will cause an upward force on the ball. However, at another instance, the same region will now be a low pressure zone, and thus cause an equal and opposite downward force on the ball, which will over time will cancel out. So there must be some other force acting on the ball, that when averaged over time will still be positive. The root of this force lies in the concept of nonlinear acoustics. When sound travels through air, the wave of pressure creates local zones of higher temperature depending on the amplitude of the wave at that point. Thus, where the amplitude of the wave is larger, the wave will move more quickly, and because of this, the wave has a nonlinear nature. Therefore, the pressure created by the wave can be expressed in the form of a Taylor approximation of the pressure as a function of the density of the particles in the air. And since our second order term of this approximation will be squared, it will always create a positive pressure and thus a time-averaged positive force, which at large amplitudes will balance out gravity and thus allow for a levitation to occur.